All right, good afternoon, everybody. Great to see the room with all these interested people in vector technology. I'm Mark Throndson. I work in the product team at SiFive, specifically on the core IP RISC-V compatible product lines. And we called this the SiFive vector processor presentation. I'm actually going to be talking about our vector processor roadmap and software development activities, and I think and hope that you'll find it very interesting. All right, so first of all, SiFive has been heavily involved and is investing in making the vector extensions and vector technology within the RISC-V community a reality and successful. It's interesting that the inventors of RISC-V were driven by the desire to have an open architecture that could be used for computer research. And one of the key areas was actually vector research. And now we've, as RISC-V has gained momentum and is plowing forward, the vector extensions to that base architecture are being fully put in place. So I wanted to talk about, just for a moment, about the fact that the SiFive team is actually contributing to helping build out not only the ISA itself, where Krista is chairing the vector extensions working group and driving the spec collaboratively within the community, but also to point out that we've developed the vector extensions to the assembler and to the Spike instruction set simulator model. We did those actually as internal projects at SiFive and then contributed them to the open source community. So we're very motivated and excited to try to bring this to reality, and we believe 2020 is the year that all converges on solutions. And part of that is actually building commercial solutions based on the underlying technology, and that really leads to our SiFive intelligence processor line. So what is a SiFive intelligence processor? Well, really, in the plural, it's a portfolio of RISC-V core IP with vector intelligence. And that starts with support for the RISC-V vector extensions. This is being defined in a way to be highly scalable, both in software and hardware. So it's really not meant to be, I'm implementing at a very high-end processor or just a small extension for very entry-level processors. It's really meant to scale. And that scalability comes with binary compatibility. It also delivers on being able to develop complete solutions for scalar and vector processing within a single development environment. So the second aspect of the intelligence processors is that we've got a 2020 portfolio extending from microcontrollers up to robust application processor footprint solutions coming out. I'll talk a little bit more about those shortly. But the third aspect is, and I sort of touched on it, but really we think the whole scalability of the architecture aligns very well with some of SiFive's fundamental advantages and capabilities in how we build processor technology. You have scalability in software, and we marry that with our microarchitecture development to provide highly scalable, configurable solutions. So this is our roadmap for the vector intelligence processors. It is loosely temporal, as in going from left to right. It follows time. And and it covers a variety of footprints in terms of where it provides solutions across a very wide range of vector applicable technologies, from IoT applications all the way up to the data center. The first product, and the only one that I'm really going to touch on any additional layer of detail today, is the VI2 Series Core. And just to give you a taster for today, it actually is very extensible and applicable to a variety of markets. As an initial focus, we've been developing solutions really targeted for the smart voice and audio market space. But it's applicable for general DSP applications and many other applications beyond that. As such, it has element data type support common to DSP, AI, and general compute applications, which essentially is integer, fixed, and floating point data types from 8 to 32-bit widths. As you would expect, it builds on the RISC-V vector extensions, and it's really, again, it's leveraging that scalability that's built into the architecture. To deliver the performance of what a vector compute engine can do, we actually incorporate separate data paths for the scalar pipeline and the instruction pipeline. The initial default configuration, and I'm telling you this today because we have some initial performance points that I'll share, it's basically a 128-bit wide data path with a 512-bit vector length per register in a 32-register architecture. And using LMUL, you can actually extend that to working on vectors as long as 4,096 bits. But again, need to stress, it's configurable ultimately, and so the points that I'm talking about there are for a specific initial default configuration. And you can build technology, but you also need to be able to evaluate how your code's doing and debug it and trace it. And this solution actually plays directly into our existing debug and trace hardware solutions. So it can work easily with our third-party tool offerings, and we're talking with some of those vendors already in support of this. And within our own Freedom Studio tools, things like visibility into the vector registers and control registers are part of the solution. Okay, so let's talk a couple slides on performance. So, and I'll talk about this next aspect a little bit more a few slides later. But we've actually developed a DSP library with vector support that support the RISC-V vector extensions, and this gives a mapping at a loose level in terms of bucketizing the different functions across different operations in the library. The net of it is all of this is being measured on 32-bit floating point data types, and we see greater than a 9x speed up across the suite of DSP functions there. And this is actually done on very small data sets. I would consider this probably a conservative view of what you can see if you scale up the data set size further. Oh, and just for full disclosure, this is comparing vectorized assembly versus scalar source compiled to the CPU. So more specifically, matrix multiplies are a big part of many application spaces, including the whole AI and neural networking arena. Using that same library, 32-bit floating point workloads in this particular point, and doing matrix multiply on a 256 element, so 16 by 16 arrays multiplied together, we see better than 22x performance scaling between the vector extensions and the scalar, associated scalar performance. And you can see, you don't need to read it today, but basically you've got the scalar C code on the left and the vectorized assembly on the right. And this is actually with the scalar code unrolled without the unrolling, and that obviously, when you unroll code, you expand the code size. I believe the code size increase between these two scenarios was about 2 or 3x, so it was pretty dramatic. When you don't unroll the code, it's another 10x faster on the vector core. So very significant difference. And really, those couple examples lead me to what I think you may find interesting, because we've not only been developing hardware, but we've been investing heavily in the software side. And our vector evaluation platform is really our first vehicle for enabling the algorithmic evaluation and porting efforts with the community and with customers and partners who want to test and evaluate their algorithms on the RISC-V vector extensions. So it's actually comprised of a number of key tools and elements. One area is the tool chain itself, and that's a vectorized assembly or assembler. But it also includes a GCC compiler and Intrinsics that SiFive has developed for vector support. To complement that, I showed you a couple examples from the DSP library. There's a DSP, optimized DSP library. We wrote this with the idea of being compatible with the Simsys DSP AIs for those people utilizing those APIs and software model. It should ease ability to pull in use of the vector extensions. And then in select cases, and we will continue to add to this, we've done even more highly optimized FFT kernels and matrix math kernels. So we're spending a lot of time on the software side, not just on the hardware side. And as targets, we support both a performance model and the Spike instruction set simulator golden reference model for the RISC-V community for actually running the software. Key is it's actually available now, so please contact us if you're interested in getting access to this platform. I'm not going to go through lines of code here. The point I really wanted to show is I made the claim on the last slide that we've developed vector intrinsics support, and this just gives you a quick snapshot of an example vector addition implementation using the intrinsics on the left. Obviously, the pound include statement are the intrinsics, and then the actual intrinsic statements are embedded in the code, color-coded, and the corresponding generated assembly on the right. So, I only had 20 minutes to talk to you today about this topic, but I did want to summarize a few key takeaways from the talk and then give you a few minutes for any questions that you might have. The first is, I just want to reiterate, I think the vector technology within the RISC-V community is becoming real. It is 2020 is the year of the vector for RISC-V, and we have big plans to not only make that a reality, but also to invest and make it successful. Part of that investment and reality is our delivering on a roadmap of SiFive intelligence processors covering a wide range of implementation points and use cases. Our focus on investing in not only hardware, but also software to enable solutions around the vector extensions. And really, first snapshot of that is our introduction of the SiFive vector evaluation platform, which is here to enable evaluation and porting and development for hardware and software around vector technology. And that's really my last point. It's a call to action. Software partners, algorithm developers, whether you're sitting here today or looking at my presentation later, please contact SiFive to help vectorize your solutions for RISC-V. And with that, I thank you very much, and I open up the room for questions. Yes?
Did you implement the full vector extension ISA?
The question was, are we implementing the full vector specification? So depends if you're talking core or the portfolio, but the top level answer is over time, yes. As an example on the VI2 core, however, I mentioned the data types that are supported. We're not supporting double precision floating point. And initially, working with customers, we have made some choices, but over the medium term, the answer is generally yes.
Is there a target frequency?
Target frequency? So the question was, is there a target frequency? That's a very core dependent question. We'll be revealing more details about each of the individual cores as we fully announce them in 2020. But I guess as a general statement, I can say that on the vector implementation of the VI2 core that I showed today, we do not see it being appreciably slower than the existing 2 series lineup in the SiFive portfolio. Yes? I think I heard the question. The question was, will we have open BLAS support for the SiFive vector cores? I think high probability yes, probably even more than high probability yes. I'm not going to give a specific timeline today, but next year is probably a good guess.
How many vector instructions can be dispatched per cycle?
Question was very much a microarchitecture question. How many core or how many vector instructions can be dispatched per cycle in our cores? And we'll reveal those details on a core by core basis. But the VI2 core that I showed, one layer of detail. When you see separate data paths and things like that, it should, generally we're implementing several execution engines for different parameters. So the actual instruction fetch, decode, issue aspect is common, but beyond that, you can see a lot of parallelism in execution. Yes, especially across the range that I was showing today. Yeah. So I'm going to paraphrase here, but I think the general question was, What did I mean exactly when I said 128-bit data path versus, it was actually 512-bit vector register length. So I'll just elaborate on that if that was your question. Yeah. So when I say 128-bit data path, I'm effectively telling you that it can basically do vector operations at 128 bits per cycle to complete a full 512-bit vector, which is actually the length of the physical, each physical vector in the vector register file. It takes 4 cycles to do that. Yes? Well, so the physical vector length is determined in hardware, but you can actually program in software what length of vectors you're actually operating on. Alex, you want to say that louder so everyone else can hear?
Okay, so it's CSR.
Yes, it's a CSR. Hey, Sanjay. I'm sorry? How many registers in the vector extensions? So the vector extension specification is for, basically it's 32 registers.